So, as I've said before, we are taking regular languages slowly, step by step, because regular languages represent kind of the simplest kind of languages that we're going to be using. And once we do all these different things with regular languages, we will see how we can do the same things with more complicated languages, and we'll work our way up very quickly, really, once we finish doing regular languages, to talking about pretty much anything you can program on a computer. But we have one more topic we need to talk about with respect to regular languages before we move on, which is regular grammars, which is yet another way to describe regular languages. And the book assumes, when you get to the section on regular grammars, that you've already learned about grammars, which I'm not going to assume. So we're going to do a little bit of an introduction to grammars in this section, and then we will go on and talk about regular grammars in particular. So everybody's familiar with English grammar, and if you have a sentence like "the big dog chased the cat," then we can split that sentence into subject and predicate, and we can split the subject into an article, an adjective, and a noun, and so on. And there are very specific rules for English grammar. Of course, English grammar is much more complicated than the grammar of many languages, but we could say that in order to create this sentence here, what we had to do is we had to say, well, a sentence is made up of a subject followed by a predicate. And what's a subject? Well, a subject is built out of an article followed by an adjective followed by a noun, and so on, right? So we can talk about the rules of English grammar, or at least the rules for constructing sentences like this. Now, sometimes even linguists who are studying English will draw a parse tree for this kind of sentence. And so in the same way that before we said a sentence is made up of a subject and a predicate, we just draw that out using a tree structure, right? So our sentence is composed of a subject and a predicate. Our subject consists of an article, an adjective, and a noun. And eventually we get to kind of the leaves of our tree, which are the actual words that we're using. So if you look at this, all of the leaves on the tree are words in the English language, and the internal nodes on the tree are parts of speech. Okay? Or grammatical predicate isn't a part of speech, is it? My English grammar is not fantastic. So grammarian terms, we'll call it, or something. But the important thing to note here is you start with your sentence, you break down into the different parts, and all of the internal nodes in the tree are kind of in one class of things, and the terminal nodes of the tree, right, the leaves of the tree, are all actual words in the English language. So now let's talk about the grammar for an arbitrary language, keeping in mind that now by use of the word language, I mean a set of strings, right? If I say to you, at least for the rest of this semester, what's a language, you should just instantly blurt out at this point, it's a set of strings, okay? So if we have L as a language over in alphabet A, then we can talk about a grammar for L, which is a bunch of grammar rules, right? And they all take this form. And the form is one thing, arrows, another thing, okay? So in this case, we've got gamma arrowing delta, right? So, and we say gamma and delta in this case are strings of symbols, and these symbols are in my alphabet A and also from my grammar symbols, which are disjoint from A. So this is the formal definition of a language. Let me show you what I mean. I think when you see this example, it'll make sense to you. So let's let A be the alphabet consisting of the symbols A, B, and C. And we're going to say S is our start symbol. So here's a grammar for A star, keeping in mind that A star, remember, is the set of all strings over this alphabet, right? So anything we can come up with. So when you start, you either end up with lambda, or you end up with A followed by something made up of S, B followed by something made up of S, C followed by something made up of S. Let's look at let's try and derive the string CCAB, right? And then you'll see what's going on here. So what I can do is I can say, well, if I start with S, you always start with your start symbol. From S, using this last rule here, I can derive, and we're going to use this double arrow, CS, right? So effectively, I took this single S and expanded it using one of the rules into CS, right? And now from that one, I'm going to expand that into CCS, because again, what I did is I took this single S and I turned this single S into CS using this last rule. Okay. I think what I'm going to do is shrink this a little bit so I have a little bit more room. Let's get that up there, and we'll take this, move it over here. Okay. And so remember, I'm trying to derive CCAB. So now, I think you know where we're going here. I'm going to do CCAS, because of course, what did I do? I took this S and I expanded it into an AS using this second rule here, right? And still I don't have enough room, so bear with me. I'm going to do a symbol that is not really part of grammar symbols, but you'll get it. All right, so we'll arrow up to there, and we'll expand that last S into a BS, like so. CCABS, because this S is going to expand into BS. Notice, by the way, the stuff I'm writing in red here is not part of my derivation. I'm just trying to show you what kind of gets expanded. And we're not quite done yet because we still have this capital letter S in here. And the things on the left-hand side of this grammar, which in this case are all just S's, we call non-terminals. They're like the internal nodes on our tree. They're not part of our alphabet, so we can't stop there. So what I'm going to do is I am going to say, well, that one goes to CCAB lambda, because of course we can take S and turn it into lambda using this rule up here. And so now if you look, I've derived CCAB lambda, but CCAB lambda is exactly the same as CCAB, right? And so I have derived CCAB using these rules. Here's a cleaner version of what we just did together as a group, and you'll notice that in here I tell you that this arrow means derives in exactly one step. So this these lines like you know, S goes to BS, that's called a grammar rule or a production rule. And when we're talking about in here, if we have gamma arrows delta, we can say gamma produces delta, or replace gamma by delta, or gamma rewrites delta, or gamma reduces to delta. And in fact, you've heard me already informally, it's not so accepted, but I'll say something like gamma goes to delta, or gamma, I often say expands to delta, even though reduces to is the more polite way to say it, the more official way to say it. So in here I would say S produces BS, or S reduces to BS, or one of these. And so just like a DFA or an NFA always has to have a start node, Every grammar has to have a special grammar symbol called the start symbol. And you have to have at least one production rule. This is one production rule, but there must be at least one production rule that only has a start symbol on the left-hand side. You can have just one, or you can have more than one. And as we've seen in our grammars before, we had the start symbol on the left-hand side in several production rules. And you know, you've probably figured out that you can have a parse tree for these kinds of derivations too, right? So if we say we start with S, we get this S up here, that reduces to AS, right? And so you can see we have the parse tree for our AS, and then and that's just kind of showing you that this piece S goes to the AS, and then this piece S here, right? So that S on the right here actually reduces to BS, and so on. Okay, here's the formal rules, the formal definition of a grammar. Some of this will make more sense as you see more grammars. But a grammar is going to have a finite set of grammar symbols that are called non-terminals. These non-terminals are basically the things that are not in the alphabet, right? And they are also on the left-hand side. I'm writing LHS for left-hand side of my rules. Okay, that's the non-terminals. They may appear on the right-hand side too, right? But definitely on the left-hand side. We also have a finite set of symbols called terminals. These are going to be the letters in our alphabet that we're using in our language. And our non-terminals and terminals have nothing in common. One of our non-terminals will be called the start symbol. It doesn't always have to be the letter S, though we will often use the letter S. And then we need a set of production rules. Notice that we say finite. You can't have an infinite set of production rules. And they take the form that we've seen, where it's gamma arrow delta. And effectively, what this stuff down here is saying is, look, gamma, the thing on the left, can't be empty. You've got to have at least one rule that has S by itself on the left-hand side. And all of the non-terminals have to be on the left-hand side of some production. So the non-terminals have to be on the left-hand side. They have to be expandable. Again, let's look at some more specific examples. It'll probably clear this up, and you can come back and look at this slide again in a couple minutes. Just one point of clarification. We have always said that lambda can never be part of an alphabet. Okay, and we're going to continue to say that lambda is the empty string. It's a special character. You are not going to find it in any alphabet. But just to be clear, in order for us to be consistent with the book, we're going to say that if lambda is a part of a grammar, then it's one of the symbols in the set of terminals. Okay, so generally our terminals are just letters of the alphabet, but it may also, our terminals may also include lambda. All right, so just this final line will continue to say that lambda is not a part of our alphabet from which we take symbols for our strings in our languages, but can be one of the symbols in our set of terminals. Now, it is possible for a grammar to have more than one non-terminal on the left-hand side, and there's nothing about our rules for grammars that say that you can't have terminals on the left-hand side as well. But for the purposes of this class and for everything that we're going to be doing, we are only going to have a single non-terminal on the left-hand side. So that's kind of note 1. And note 2 is, you know, computer scientists like shortcuts, and mathematicians like shortcuts too. And so what we're going to do is, if we have a bunch of rules that have the same non-terminal on the left side, so for example, all of these rules have the non-terminal s on the left-hand side, right? We can combine these rules by just saying s goes to lambda or as or bs or cs, right? And here we go again. We're using this bar symbol to represent yet another thing, right? We've used bar symbol in our sets to say x such that x is less than 5. We've used the bar symbol to talk about the size of a set, right? We've used the bar symbol for a bunch of things, and now we are also using it as our divider for these rules. And sorry, you just need to be able to kind of tell the difference from context. So now we just need to talk about how do you build a grammar, right? And so, you know, how do you use your wits to make a grammar? And it's just to kind of, you know, how do you think about building these things up? So let's just talk about this, and let's do a few examples. So this first example, and I'm just going to give you the production rules. I'm not going to give you the 4 tuples. So let's look at this first one. We need to find a grammar for the language a to the n such that n is an element of n, right? That's the same as saying we're finding a grammar for a star, which we've done before. It's you've probably remember how to do this one, but we're just going to say, well, you're going to start, and either you're going to go to an a followed by the start symbol again, or you'll go to lambda. Yeah, it's pretty easy, right? Because we just keep kind of building up the a's. This next one, a to the n, b to the n, right? So 0 or more a's and b's, right? So 3 a's, then 3 b's, or 27 a's and 27 b's, or lambda, the empty string, right? And in fact, no, this is not a regular grammar. But just because it's not a regular grammar, remember, we're not doing regular languages right now. We're just doing, we're not doing regular grammars right now. We're just doing grammars. And so, so we can do a grammar for this. It will not be a regular grammar because our language is not a regular language. But that's okay. So when you're doing something like this, a to the n, b to the n, you need to kind of think about how you build it up. The important thing is every time you add a as a non-terminal, you have to add b as a non-terminal. And what we can't do is we can't do something like this. We can't say s goes to abs. As a production rule, because then we could get something like s goes to abs, goes to abs, which would mix up the order of our a's and b's, right? And here it's all the a's come first, then all the b's, right? A to the n, b to the n. So that's no good, right? So we can't do that. So let's get rid of that and try again. Okay. So what we're going to do is we need to have the same number of a's and b's, but we need them to kind of bubble out from the middle, right? So our rule is going to look something like this. We're going to say s goes to ASB, right? So every time we put that s in, the a's are on the left and the b's are on the right, or lambda. And if you look at that, then if I'm trying to derive a string like AABB, you'll see what we get is we get something like S goes to ASB, goes to AASBB, goes to AA lambda BB. And we got it. So that's pretty good. Okay. Finally, let's do this last one. Now we want AB to the n, right? The language AB to the n, and that is in fact a regular language, right? So it's just a bunch of ABs, 0 or more ABs. And that was in fact what I wrote in red before, right? So we're going to say S goes to ABS or lambda, right? So every time we put in our letters, we'll put in our ABs, and then we could expand some more if we wanted. I don't expect that finding these three languages for this first slide would be easy for you. It does take a little bit of practice to understand how these things work. I think what you need to kind of really look at and really note here is the difference between how these three grammars work, right? So this first one is just a single letter building it up. It's pretty easy. And in fact, you know, you might want to note that we could also have said this goes, S goes to SA or Lambda, right? Nothing wrong with that. And similarly for this last one, we could have said S goes to SAB or Lambda. That would have been fine. But this middle one, where we really need to kind of build it up from the middle, it's almost like I keep thinking of it bubbling out of the middle. It's really important that we get that S in the middle. We're expanding from the middle. But the good news is we're not going to have to do that kind of weird bubbling out just yet, because the language A to the N, B to the N is not regular, and those bubbling out languages are not regular. And for now, we're going to talk about regular grammars and what makes a grammar a regular grammar. So here is the formal definition of a regular grammar. We say that a grammar is regular, it's a regular grammar, if all of our production rules look something like this, where the capital letters are non-terminals and this omega is some non-empty string of terminals. Okay, so we can have a non-terminal going to lambda. We can have a non-terminal going to this omega, some string, right, non-empty string. We can also have a production rule that has a non-terminal going to another non-terminal, right? And we can have a production rule that says we have a non-terminal going to a non-empty string of terminals followed by a non-terminal. So what's special about this that makes it a regular grammar and not just any old grammar, right? There's two key things here. The first is that there's only one non-terminal on the right-hand side, right? So if you look at these, you can have a string of terminals, right? But all of these rules, the only ones that have a non-terminal on the right-hand side are the last two, right? Sorry, and yes, they're the only ones that have a non-terminal on the right-hand side. And furthermore, there's only ever one non-terminal on the right-hand side when there is one. And in addition, if there is a non-terminal and there are any terminals in there, the non-terminal has to be to the far right, right? So if you look here, there's either a non-terminal by itself or a non-terminal that's at the very end, right after the string of terminals, right, the non-empty string of terminals. So this means we can't do that bubbling out trick that we've been doing for making those languages that aren't regular. Okay, so we've talked about these rules that tell you what makes a grammar a regular grammar. Let's look at these examples and see which of these are regular. Well, this first one is not regular because it's got that B in the middle there, right? That capital B, a non-terminal, which is not at the far right of the right-hand side of that production rule. Okay? Let's look at the second one here. Again, it is not a regular grammar, right? It's not a production rule that could be part of a regular grammar because we have two non-terminals there, right? And you can't have two non-terminals in a on the right-hand side or on the left-hand side, for that matter, of a regular grammar of a production rule. This last one, however, looks good. What have we got? We've got a string of terminals followed by a non-terminal, which is just this form. So that's a production rule that's that is of a form that could be part of a regular grammar. Now, one thing I just want to clarify about this last rule here is it's okay for to have something of the form S goes to, say, AS. There's nothing in our rules that says that S and T cannot be the same non-terminal. Our rules just say that S and T have to be non-terminals. So don't be stressed out if you see something like that. That's also part of a regular grammar. Right? And you'll notice that in this example we just did, we have A on the left-hand side and A on the right-hand side as non-terminals. That's okay. There's nothing in our rules, go back a slide, nothing said that S and T cannot be the same non-terminal, right? So this is perfectly legal. Now, it is really important to note that grammars are not unique, right? You can have two different grammars for the same language. We've seen that before, right? And there can be two different regular grammars for the same language too. You shouldn't be surprised by this, right? While we said that there is one minimal state DFA, right? We know that there's a ton of DFAs that recognize the same language, right? So for example, if we look again at that DFA that we had before for A star B, right? Here was our DFA for A star B. We had our start, and we had A looping, and B going to state 2, and then we had our kind of garbage state over here, which had an A, B loop, and that was A, B. So that's that's a minimal state DFA. But what if I added state 4 here, and I said state 4 looks like that? That's another DFA, recognizes the same language, right? Just because you can't get to 4 doesn't mean that you can't have it, right? I mean, you could have, there's state 5, which just loops on itself. Still, all 5 of these states, that's a totally valid DFA. There's nothing that says all our states need to be connected. So that's a completely valid DFA that recognizes the language A star B. So just because there's a single unique minimal state DFA doesn't mean that there's a unique DFA. There's a ton of DFAs. Actually, more than a ton, an infinite number, right? We can keep adding nodes as long as we want to. So let me squidge that down and make this one back to full size. So, you know, we can have two different NFAs for the same language. We can have two different DFAs for the same language. There can be multiple regular expressions for the same language, right? So another regular expression for A star B is B plus A star B, right? So you can have a B on its own, or an A followed by 0 or more A's followed by a B. I mean, that's a regular expression. Another regular expression for the same language is just B plus A star B, right? Because it doesn't make a difference if we repeat something, right? These are all perfectly reasonable. And the whole point of this slide is just to tell you that grammars are not unique. There can be two different grammars for the same language, so don't get stuck on that. There can be two different grammars for the same language, and there can be two different regular grammars for the same language as well. So let's see what happens. Does this shrink everybody now? Yeah. Woohoo! So let me just show you two grammars for the regular expression A star B. Okay? Here's one grammar, a regular grammar for A star B, which would be S goes to AS, and S goes to B, right? So as many A's as you want, and then you end with a B. And of course, this language, these production rules here that I've just circled, that's exactly the same as saying it in one line, right? S goes to AS or B. Just to remind you, we can do it in one line. But we can do this same rule. Let's change colors. We can do this same rule. We can do this same grammar. So we can represent the language A star B with a different grammar. We could say that S goes to AS or AAS or B, right? It's certainly a different grammar, different production rules, right? This one has 3 production rules. The previous one has 2 production rules. The purple one has 2 production rules. And this just says you get to choose when you add your A's. You can add 1 A at a time. You can add 2 A's at a time. Both of them represent the language A star B. And my reminder was ahead of time. Just remember that this notation here is just a shorthand, right? Computer scientists like shorthands. Apparently people who write books about discrete math like using this bar symbol to represent everything from size of to our such that, you know, in a set x such that blah blah blah. So other than the fact that we use that bar symbol for just about everything we can think of, it's important to remember that we're just using a shorthand here. If you have a rule that looks like that, oops, I'm not circling it very well, you just want to think in your head, oh, that's shorthand for these 3 rules, right? Just remember that. Now, there are some things that can be very difficult when you are trying to work with regular grammars. For example, suppose that you have a grammar for A star. Here's a grammar for A star. It's pretty easy, right? It's a regular grammar where A is my start symbol, and there's just 2 rules. A goes to little a big A, or A goes to lambda. And I can have a similar grammar for B star. It's just B goes to little b big B, or another rule, B goes to lambda, right? Individually, these are pretty easy. But I can't just squish things together if I want to figure out A star, the language for A star, B star, right? I mean, it would be really nice if I could just say, well, S goes to the A part followed by the B part, and here's what my A part of my language is, and here's what my B part of my language is. But of course, if you look at this first rule, S can't go to AB because these are both non-terminals, and a regular language has to have only one non-terminal on the right-hand side. But we know that A star, B star is a regular language, so there's going to be a regular grammar for it. We're just going to have to look harder to find it. So you may want to pause this video for a minute just to see if you can figure out a regular grammar for A star, B star. My hint is work on it from left to right, but now let me just show you. So here's my regular grammar for A star, B star. I'm going to say that A goes to little a big A or B, where B is another non-terminal, right? That represents 2 production rules, both of which meet the rules for regular grammars. I'm going to say B goes to little b big B or lambda. So that's a pair of production rules. No, I'm sorry, that's 4 production rules, right? Because these ones actually expand. These are shorthand. But I believe that these 4 production rules will generate the language A star, B star, right? But it is a regular grammar, not, well, it is a regular grammar and a general grammar, whereas the previous grammar we were looking at wasn't regular. I'm also going to point out that for this example, I wanted to start with something that was not S, because we're always starting with S. And I wanted to show you an example of something that doesn't start with S. Remember, our rule is that the first production on top is the one that you start with. So in this case, if we were to expand these rules, it really is A goes to little a big A goes to B goes to little b big B, B goes to lambda. So if we just give the production rules and we're not actually giving the full 4-tuple for our grammar, we say that our start symbol for this grammar is A, right? Because A appears here on the left side of the first rule. So here's another regular grammar problem. We want to find a regular grammar for the language A star, B, C star, D. Again, you know, my hint is just to work from left to right. It's very similar to what we did before. You may want to pause the video and try and figure it out. I'm going to do it for you right now. So let's see, I'm going to start with S for a change, or to get back to normal, and I'm going to say, let's see, S can be little as, or it can go to, and what I'm going to do is I'm just going to say it can go to the rest of this stuff, right? And I'm going to call the rest of this stuff B, right? And the rest of this stuff is just B, and I guess B is going to go to a little b followed by a c, where I'll call C this rest of the stuff. And to do the C part, well, now I'm just trying to do C star D, so C goes to little c, big C, or we could end with a D, right? All right, here's some regular grammar problems from the book. Find a regular grammar for each of the following regular expressions. So let's see if I circle these. So we'll start with A plus BC. Again, consider pausing the video and doing all of these, or pause the video in between them so that you get some practice. But for A plus BC, I'm just going to say S goes to A or BC. Trivial, right? The next one is AB star plus C. So one option is S could just go to C, right? The other option is S could go to an A followed by the rest of it, which I guess I'll call A. And that A rule is going to have to represent my B star part, so I'm going to say A goes to, let's see, it could go to a BA or lambda. All right, so that's that stuff. Let's pick another color. I don't have that many good colors in here, unfortunately. Let's do the next one in black. So now what I'm going to do is I'm going to do this language here. Oops, I just overwrote it. Which is A star BC plus AC. So let's see. For starters, I could just say S goes to AC, right? Because that's the easy one. And now I need to do the rule for A star BC, so S goes to AS or B. And let's see. And in fact, I could write S goes to AS or little b, big B if I'm feeling lazy, right? And then big B goes to C, big B, or lambda. I think that does that one. And we'll do the last one in red. Ooh, there's a concatenation. So you got to start with an AA or a BB, and then you have to end with AA or BB star. I see. So for this one, it's you have to have at least one AA or a BB, and then as many more of them as you like, right? But you can flip back and forth between them. So this one's a little tricky. Even if you didn't pause for the other ones, pause for a minute. So let's see. Instead of starting with S, let's start with Q for a change. So Q could go to AAQ or BBQ. And really, that's going to give us as many pairs of A's or pairs of B's as we want. Because remember, what do we got here? We have, you have to have at least one AA or one BB, and then you follow that with 0 or more of whichever you like. So the trick here is going to be ending. We can't say Q goes to lambda, right, as another rule, because that would mean that that lambda would be in our language, right? We can't have lambda in our language, so that's not a rule we can have. So what we need to do here is we need to say, when you're kind of done with making as many extras as you want, make sure that Q goes to either an AA or a BB. And again, let me just remind you that all of this stuff, this is actually 4 production rules, right? So my production rules for this are Q goes to AAQ, Q goes to BBQ, Q goes to AA, and Q goes to BB. So this thing in here, just a shorthand for these rules. All right, some more problems from the book. Find a regular grammar for each of these. So we'll start with purple. This one's easy, right? This is just a finite number of strings, right? So we could say, you know, maybe I'll start with A here, and I'll say A goes to AA or AB or AC. The next one, let's see, what have we got? We have, it looks like what we have here is odd numbers of A's, right? So you can have 1, 3, 5, or A to the 2n plus 1. So if n was 3, let's see, if n is 0, then it's A to the 1. If n is 1, it's A to the 3. If n is 2, it's A to the 5, right? So this is kind of odd numbers of A's, right? So let's think about how we would do that. In fact, pause the video for a minute. Think about how you do that. And the way I think about this one is it seems to me that you have to kind of always put down pairs of A's until the end when you have to put down a single A. So I'm going to have this set of production rules start with B, just because I want to show you that production rules can start with whatever the heck you want. So I'm going to say it could go to 2 A's followed by a B, or just a single A. And I think if you look at that, you'll see that that'll generate our whole language. This next one, its bark is actually worse than its bite. It looks kind of nasty, right? It's A to the n union B to the n union C to the n, right? The regular expression for this would be A star plus B star plus C star, right? And you should be able to do that in your head, right? You should be able to look at this and say, oh yeah, that's what this is. So what I'm going to do, let's start with capital D now. I'm just skipping C because lowercase c and uppercase c is hard to distinguish sometimes. So, so I'm going to do it with, I'm going to have my first production rule start with D. And what I'm going to do is I'm just going to, since this is 3 different sets of strings we need to generate, I'm going to say D goes to E or F or G. Now remember, that's perfectly legal, that's regular, because this is actually a shorthand for 3 different production rules, right? And now, it's not too bad, right? E is going to be my A, so E goes to AE or lambda, and F goes to BF or lambda, and G goes to CG or lambda. Okay? And so now we just have to do that last one. I guess we'll switch back to purple again. So we're doing this last one, A to the 2k such that k is an element of n, unioned with B to the 2k plus 1 such that k is an element of n. Ouch, right? So what have we got here? Think about it for a minute. Pause for a second and think about what is the regular expression, right? What have we got here? So on the left, this piece here on the left is pairs of A's, right? So it's going to be AA star. And the one on the right is odd numbers of B's. So, you know, k starts at 0, and then we have 1 B, or k is, if k is 1, then we have 3 B's. So I'm going to say it is BB star B, right? And so again, let's see, we were up to G. So let's start this set of production rules with H. And I'm going to take each of these two sides in turn. We'll start with this left one. I is a weird capital letter too, so we'll go to J or K. And we'll do that AA star for the J part. So J is going to go to pairs of A's followed by a J or lambda. And K, which is the other one, is going to go to pairs of B's followed by a K, or in this case not lambda, but we end with a B, so we get that odd number. And finally, we have some even more tricky problems from the book, right? So find a regular grammar for each of the following languages over the alphabet A, B. So strings that have a length that is a multiple of 3, and strings that have an odd number of A's. So pause the video and think about the first one for a minute. We'll do the first one in purple. So pause the video for a minute, think about it. So it helps me to think about the regular expression that represents these things. And a length that's a multiple of 3 means that we're going to have to put down chunks of A's and B's where there are 3 of them. And the easiest way that I can think of for a chunk of A's and B's with 3 is to just kind of list them all out. So we got AAA, or AAB, or ABA, or ABB, or BAA, or, wow, there's a lot of these, huh? BAB, or BBA, or BBB. Did we get them all? It should be 2 cubed, which is 8, right? Because there's 2 possibilities for each space. So 1, 2, 3, 4, 5, 6, 7, 8. Woohoo! I think we got them all. So that's the a regular expression if we just wanted one triple of letters, but I want multiples of triples of letters, right? And 0 is also multiple, so I want 0 or more of these. And so the regular expression I'm going to use, and just pretend this is all on one line, all right? Is this thing starred, right? So, so how do we do that as a grammar? Well, it's going to be messy, but it's okay. We could say something like S goes to AAAS, or AABS, or ABAS, or ABBS. Let's start again. S goes to BAAS, or BABS, or BBAS, or BBBS. And that gives us the as many as we want, and then we just have to add an or lambda so that we can stop, right? And we have a string when we're done, and also we can have lambda, right? Because lambda is a length that's a multiple of 3, I think. So it's a bit ambiguous, isn't it? I suppose you could argue that it's not a multiple of 3. If you don't think 0 is a multiple of 3, then what you would have to do is you would have to say, all right, scratch that lambda, and I have to end with one of these guys again, so AAA, or AAB, or ABA, or ABB, or BAA, or BAB, or BBA, or BBB. I fit them all in. So you decide. If the language we're talking about is this one that I wrote up here, this regular expression with the star, then you want to get rid of this last line and include lambda. And if you want to have multiples of 3 where there's at least, 3 there, you're starting with 3, then you get rid of lambda and you include all that stuff. Okay, so that's the first one. Now let's see if I can shrink that. Actually, I think it's messy enough that I'm just going to erase it all. Bear with me. Oops. Now we got to erase this piece. There we go, very good. Okay, so now let's do in blue all strings that have an odd number of A's. And again, pause this for a second. So this is over the alphabet A, B, remember. So we can have as many B's as we want, but whenever we have an A, it's got to be an odd number of A's. So this one's a little bit weird. It would be, I don't know if it would actually be easier if we were trying to do a grammar that wasn't a regular grammar. But here's what I'm going to think about it. We have to build the string up somehow, right? And at any point in time, that string is going to either have an even number of A's or an odd number of A's. And I'm only going to stop when I get an odd number of A's. Okay? When I can only let myself stop generating the string when I have an odd number of A's. So what I'm going to do is I'm going to say that we can start when we have our first production rule. 0 is even, right? So we're going to start. I'm going to have two production rules that I'm going to, let me put it up here in the corner just so I'll do it in green. I'm going to have E represent, I currently have an even number of A's in my string. And I'm going to have D, because I don't like using O as a production rule as a capital letter, to represent I have an odd, right, number of A's. So if I start, I can either start with an A and immediately go into my deal with the fact that I have an odd number of A's now, or I can go straight to the even rule because I have an even number of A's. So if I have an odd number of A's, I have two choices. One, well, let's see, I have several choices actually. One is I could stop, right? I could just throw in a lambda because I have an odd number of A's. Another option is I could add in as many B's as I want, right? Because nobody said anything about the B's. And finally, if I want to add in an A, that's totally fine, but then I kind of go to the world where I now have an even number of A's. And so now we just need to finish off. If I have an even number of A's, I can add B's if I want, right? Or I can add a single A and say now I have an odd number of A's, and so I go back to that kind of odd generating rule. But I can't add the lambda here because I don't want to end with an even number of A's. So I think that's my answer. So again, go away, practice generating these grammars, more problems from the book, more problems that you make up yourself, more problems that other people suggest. Okay, and of course all the homework problems. But that's it for regular grammars. There's not a whole lot to them once you know the rules. Just like we have a formal way to represent a DFA as a 5-tuple and a formal way to represent a NFA as a 5-tuple, guess what? We can represent a grammar as not a 5-tuple, but a 4-tuple. Okay? We have a list of the non-terminals, a list of the terminals, we specify the start symbol, and we give all the production rules. Most of the time, we're just going to write the production rules. We're not going to actually use this formal representation. But again, it's something you should be able to do if I asked you to do it, right? Just because one of the things about this class that we're trying to make sure you learn is how to be very clear and very precise and very formal in your language, using language as it's normally used, right? So we want you to be skilled with being precise when you try to be, right? We want you to be able to intend to be precise and be precise. So just as an example, if my production rules are the ones we've used so far, right? So remember, this thing actually expands. This is 4 different rules. S goes to lambda, S goes to AS, S goes to BS, and S goes to CS, and we just had it written out on a single line like this to save space. Then our grammar would say our non-terminals are a set, because you could have more than one non-terminals. Right now we only have one, it's S. Our terminals are the letters of the alphabet plus lambda. Notice it doesn't say this is our alphabet. These are our terminal symbols. The start symbol, the one that we're going to start with, is S, and our production rules are P, which is specified by this, or by this. Right? We could say P, like that. So let's come up with a 4-tuple for this grammar. Remember that our 4-tuple consists of the set of non-terminals, right? The set of terminals, the start symbol, and the production rules. So for my production rules, I'm just going to write P is this thing right here. And let's do the 4-tuples. So my non-terminals are the set of all symbols that appear on the left-hand side. So that would be S, A, and B. My terminals are the letters of the alphabet and also lambda, if it exists in here, that could possibly be derived from my non-terminals. So in this case, I have A, I have B, and I have lambda. My start symbol is going to be S, and my production rules, I'll just write P because I defined P up here, right? And we can see that we could get strings like ABB out of this, right? Because we could say something like S goes to AB, which goes to AAB, right? Because I'm going to take that S, expand it into AB, take that A, turn it into AA, right? So that could go to A lambda B, right? Expanding the A into a lambda, which goes to A lambda BB, which goes to A lambda B. Oops, that's supposed to be a lambda, not an A. A lambda B lambda, which is just the string AB, right? So if you look at this grammar, you can see that it produces all strings that start with A's and then end with B's, 0 more A's followed by 0 more B's. So this grammar is actually a grammar for the regular language, A star, B star. A couple more fancy words or phrases that you should know for parties if you want to talk about grammars and sound professional. We talk about a sentential form, which is just a string made up of terminals and non-terminals. So, you know, on the previous page we had a string that looked like this. What was it? It was A lambda capital B, right? And that has some terminals in it and some non-terminals. So, you know, that's a sentential form. And you know, A lambda little b lambda is also sentential form, but you don't have to have non-terminals or terminals for that matter in your string to make it a sentential form. And then finally, you'll see on the previous pages, I've been using this double arrow notation to represent these derivations, and that just says here's how you do one step. If it is the case that gamma produces this delta, then we can take the gamma in here, replace it with the delta, and call that a derivation. More just detailed notation. The double arrow by itself means derives in one step, exactly one step. If you stick a plus on it, that means derives in one or more steps. And if you stick a star on it, that means derives in 0 or more steps. This shouldn't be too surprising. So just to make sure you're clear on this, let's do these questions from the bottom up. So can you get in exactly one step from S to AAB? And the answer is, of course, no. Can we get from S to AAB in more than one step? Well, sure we can, because I think we did it before, but let's just do it real quick. S goes in one step to AB. We can replace that capital A with a little a, big A. And we can replace that next capital A with another little a, big A. So that'll take us to, oops, sorry, little a, and then we replace the capital A with a little a, big A, and there's our B. While we'll replace the capital A with a lambda, so that goes to AA lambda B, which goes to AA lambda little b, big B, goes to AA lambda little b lambda. Oops, that's supposed to be a lambda, right? And that is the same as little a b. So we can definitely derive little a b from S. We can do it in one or more steps, and we can actually do it in 0 or more steps. It happens to be more, but 0 or more is more. Okay. Now, I showed you one way to derive AAB, but there are, in fact, other ways you can derive AAB. So, for example, here are two different derivations for AAB. And you can see that they both start out the same, right? We start out with the same first step. But then we, in this first one, we're kind of doing what I did in my example and expanding the A first. And in the second one, we happen to be expanding the
So these are some problems
B
from the book that do not have the answers. There's even more problems
as of
from
right
the book
now,
that give
nothing
you the
wrong
answers.
with doing it either way.
Of course,
it's
remember
important
that
to note that there's not necessarily
the
a
book
single
does not
derivation
give you,
for a given
the answers
string.
that the book gives you are not the only answers.
What we
Lots
will
of these
say,
can be done
however,
in lots of
is
different
that
ways.
you can have
why don't we just try
derivation
and
that
do
you call
a couple of these,
leftmost
right? So I'm not going to do them
derivation.
all, but we'll do
And when
a
you're
few
talking
just
about
so
a
you get
leftmost derivation,
some practice with this. Why don't we do
that's a derivation
first
where you
one,
always replace the leftmost
second
non-terminal
one.
first. So that's what I was doing when I was saying let's replace the capital A first, because the capital A was the leftmost non-terminal in our terminal list.
I don't know.
Right? But strictly speaking, you know, formally a leftmost
we'll
derivation is a
do
derivation that
this
at
one.
each step
Okay.
the leftmost non-terminal
So let's see, this first
of the
one.
sentential form is reduced by some production. And of course, we can also say, you know, there's another term which is called the rightmost derivation,
the
and
first one
you won't be shocked
looks
to
like
hear that a
it's
rightmost
strings
derivation
that
is the same thing in which we
it always has
reduce
an A
the
in it,
rightmost non-terminal first.
and then it has 0 or more B's in
So of
front
course
of it,
we've
right?
talked about
So this
the
is
language.
actually represented
Remember a
by
language
the,
set of strings, right? The
regular
language
expression, B star A.
represented by a regular
So
expression.
what I think I'm going to do,
for example, we've talked about the language of A star is this set.
What gets built
right?
up and what's
Because
left
there's our set
over
of
at the end. Up
strings.
till now, left over
We
at
can
the end
also,
has
of
been
course,
lambda,
talk about the
right?
the
But
language
it's not
represented
always
by
the
a
case.
grammar.
So for this grammar,
So
I think
if
we
we
might
have
actually be able
this
to
particular
squish it onto one line. Let's
set
see
of
if I can do
production
that.
rules, right?
I'm going to say
that
S
also
is gonna go
produces
to
the same language,
either
right? That's also
BS
the language of all
or
strings that are made up of 0
A.
or more A's.
Right?
And
So I build
formally,
up as
what
many
is the
B's as
language
I
of a
want,
grammar? Well,
and the last thing I
language of
do
a
is
grammar
replace that S with an A. All right.
is just
This next one, why don't we underline it?
our
in
language
green?
of a grammar
green.
is just the set of all strings X
B, A to the
such
N,
that
B.
X is
So
in
it starts and
capital T
ends
star.
with a
What was
B,
TT was our
and
terminal.
then it's got
so it just
0
says
or more A's
X is
in
a
the
string
middle,
of terminals,
right?
and
So
it's
another
possible
way
to get
write
from our
this, if we
start
were just
symbol
writing it,
to
as a
X
regular expression,
in one or more
would be
steps.
B,
Right? So it just says the language of a grammar
right?
is all the strings that
so
grammar
what I'm going to
can
do
produce.
here
It's exactly
is
what
I'm
you
going to
would
get rid of the part
think the
that,
definition of the language of a grammar would be.
that we don't, you know.
Now,
kind of
finding a
stays the same
grammar
way. I'm
for a
gonna say S goes
finite
to
language
B,
can be really simple,
and then
right?
A
So a grammar for
is
this
gonna go
particular
to
language
A,
here
A,
could be as simple as
lambda.
S goes
And that
to
way we get the B
A,
at the front and the
S
and
goes
the
to
end
B, and S
right
goes
away.
to C, And then we
S
stuff in
goes
as many
to
A's
A,
in the
B,
middle
C,
as
right?
we
So
want.
there's a grammar for
This
L.
third
I
one
haven't
here, I'm not
expressed
going
it
to
as
do,
a
but I'm
for
going to say,
tuple,
look,
of
it's
course.
exactly the
I've
same as
only
our A
given
to
you
the
the
N,
production
B to the N one.
rules.
Except
I gave you the
in
production
the middle,
rules
we're
in
not
the
going to
long
stuff a
form.
lambda.
Another way to write this.
We're going to stuff a B.
In
So
shorthand
it's
would be
the
S
same
goes
as the
to
previous
A,
example we
or
did,
B,
where you're
or
bubbling
C,
out
or
A's and
A, B,
C's.
C.
But in addition
I hope that you
to
see that
S going to, come on, we'll do it.
if you have a
real quick.
finite language, it's trivial
do
to write a
this
grammar
one.
for it, right? Even if it's a
Okay,
finite
let's
language
say
with
if I can get purple
100
So this is going to be
different
something like this.
different strings in the
S
language, you could just have
goes
100 of these
to
production rules if you wanted to.
A, S, B, or,
Of course,
oops, sorry.
it's trickier when you
S
get to
goes
an
to
infinite
AS,
language.
C,
There's a theorem that says if a
or
language
stick a
is
B in the
infinite, then some production or
Right.
sequence of productions must be
Let's
used
do this
repeatedly
next one here,
to construct
A to the 2N,
derivations,
N
right?
is an N. So
What does that
only,
mean?
we have to always add
If your
pairs
language
of
is
A's. We can have
infinite, there
0
has to
A's,
be
2
some
A's,
loop
4
in
A's,
your
and so
production
on.
rules, right? And
So this is actually
and
the
that loop
regular
might be
expression,
a direct root where
A
S,
star, right?
oops,
And again, relatively
S
straightforward.
single arrow
There's
goes
no
to
bubbling
AS,
here.
right?
It's, well, or it's bubbling
Or
from
it
either
could
side.
be something a little
S
bit more
can
complicated,
go to
like
2 A's and an S,
S goes
or
to
lambda.
AB.
Again, I'm doing
and
these pretty quickly.
B goes
I don't expect
to
that you can do these this quickly yet.
BBS,
I
right?
just expect
so
that
you have to keep,
if you
they're interdependent.
kind of follow along with me.
You probably
You
heard
will,
about the pigeonhole
and then
principle.
do a bunch
in,
of these, and also just go and do these
in
on your
discrete
own. Make up your
math.
own problems.
And
You'll be good.
the
Okay.
pigeonhole principle,
So the only
just as
one
kind
here
of some background,
that
the
remains
pigeonhole
that I
principle
want to do is this odd palindromes one.
The short
And
story for the
you need
pigeonhole
to know
principle
what
is
a
if you have
palindrome
10
is, and a
pigeons
palindrome
and
is,
9
of course,
holes,
a,
some hole has
a
to have at least 2
string
pigeons, right? If you look at our
that,
picture here, there are
the
actually
beginning
2
and end
pigeons. I
repeat.
found
So
this
here's
on
some odd palindromes.
web. I
I'll do
didn't
them in
cite
purple
where I found
over
it, which is pretty
ABC.
bad.
So
Sorry.
you have to have A.
But it's a cute picture. But pigeonholes really,
B maybe, and then we'll put an A in the middle,
if
right?
you
So
go
it reads the same way.
to the
forward,
UK, for example, instead of saying
or
put something in my mailbox,
C is also
in the
an
computer
odd
science department, they'll
palindrome,
say
right?
put
And
it in
the
my
odd just
pigeonhole.
refers to
And
the
these
number
kinds
letters, right?
of mailboxes that you find in most
whether you read it this
academic
way or
departments
this way,
where you can throw
it's the
papers
same. And this is another case of bubbling out,
individuals,
right? Whenever you put a
what
C at
we
the
would
beginning,
call
you
in
have
the
to kind of
States
put
a
a C at the
mailbox.
end.
In the
So
UK,
for this one,
they call
I'm
them
gonna
a
say something
pigeonhole.
like,
So doesn't
we're
matter
gonna
which.
start
The
by
whole idea of the
bubbling out the
pigeonhole
letters.
principle
So
is
we could
if you have, say,
bubble out an A
27
on either
pigeonholes,
side,
but you have 28 pieces
we
of
could bubble
paper,
out a B
there's going
on
to be
either
at
side,
least
or we
one
could bubble out
pigeonhole
a C
that
on
has
either side.
2 pieces of paper in it,
Right?
right?
And
You have
I
9
can't
holes,
actually fit. I will
10
do
pigeons,
some more ors here, but
somebody's
I
going to
can't
get
fit on
2
this line, so I'm
pigeons.
just going to start another line. But this is the same.
And that's
thing.
really, as long as
And
you
once
keep
we've
that
done
in
a
the
bunch of
back of your head
bubbling,
whenever you're thinking about
we
pigeonhole
can
principle,
put in the middle
it's
an
easy.
A or a B. Or
So
a
let me
C.
give you a high-level overview
so
of
what
this
I want
theorem,
you to try
right?
and
So
do
if a language is infinite,
take these
then
two palindromes
some production or sequence of productions must
and
be
make
used
up a few
repeatedly to
more
construct the
and
derivations.
confirm that what
okay?
I've written here
So here
actually
is
works.
a
And if you
somewhat
derive
loose
a few
but,
of these, I think
but
you'll
reasonable
see how this works,
version
and it'll give you a
of,
better
of,
feel for
of
this
this
bubbling
proof.
out that I'm talking about.
I'm not going to ask you to do
And I
proofs like
encourage
this,
you to
but
do these too, and
just to give
do
you
some
a
other
feel,
problems
okay?
from the book. I'm sure
If
I've
we
given you a bunch of
assume the
homework
language
problems.
is infinite, then
So let's suppose
there's
that we
no
want to
bound
take
on the length of
union
strings in the
of two
language. Strings can be
languages.
as long as
There's
we
a
want,
really,
right?
really easy
Arbitrarily
way
long.
to start this.
But that means,
or to do this.
if a string can be
and
arbitrarily
what we're
long,
gonna
then there
assume
cannot
for
be a
minute
bound
is
on the
that
number
we
of
have two
derivation steps
different
that we need to
grammars,
take in order to derive
and,
that string.
for
right?
two different languages,
But
and we want to
said
take the
that
union
we
of those
have
two grammars.
a
We want the
finite
union
number
of those two
of
languages.
production
So
rules.
maybe
That was way back a few slides ago,
we
where
have,
we said,
for example, down here,
a grammar has
language
a
A to the N,
finite
B,
number
C
of
to the
production rules.
N,
Let's call
and
however many
B to the
production
M,
rules we
A to
have
the
n.
Right? So these are two different languages.
If you pick a derivation
and I have a
that
grammar for
uses
this one,
n
and I have a
plus
grammar
1
for
steps,
this one, and I want to figure out the
right?
union of those
Then
two.
by the pigeonhole
And what I say
principle,
up here is,
we're
suppose
using
that the
n
start
plus
symbol
1
for
steps,
grammar
but
1,
we only have
G1
n
is
production
S1. So
rules.
let's do a
we must
grammar
use some
for
rule
this one
at least twice.
that starts with
QED.
S1. So we've got A to the N, B, C to the N.
Okay,
We
so
just did
here's a
that,
problem
didn't
from
we?
the textbook. It says, given the
just use
following
S1
grammar,
instead.
looks like we have two
So
non-terminals here. We
S1
have an S and
goes
D.
to A,
And our
S1,
terminals look like they
C,
come from the digits 0
or
through
B.
9. find a
And we
rightmost
need a
derivation
grammar
of the
for
string
the
7801.
second one,
so
which
they're
is
asking us
B
for
to the
rightmost
M, A to the
derivation.
N,
Let's
M,
shrink
and
this a little
enter
bit so we
natural
have
numbers.
some room.
So this is just actually the language B star, A star.
Something
right?
I guess I didn't say before, but generally we will use the symbol S
followed by a bunch
if
of
it's a
A's.
non-terminal
So maybe we'll have our
refer
second
to
grammar
the start symbol.
B.
But the other thing that we tend to do is we put whatever the start symbol is for our grammar, we make sure that the first rule that we list in our production rules starts with that, with whatever our start symbol is. But we're gonna try pretty hard to keep S as our start symbol a lot of the time.
What I'm gonna do,
but
is I'm gonna
if
say
we do have S as our start symbol, not only will there be an S as a non-terminal, but you'll also see that the first production rule will have S in it.
Capital A.
Okay. All right. So let's just shrink this down.
We'll go to little a, big A.
There we go. And let's do this. So we want to have a rightmost derivation of the string 7801.
That you can get all the strings that are in this
and it looks like that we need
0 more B's followed by 0 more A's.
If you just kind of inspect this grammar,
so
right?
let's just look at what I have here before.
Look at this
Suppose that the start symbol for grammar G1
what are our
is
choices
S1.
for S?
Well,
S can go to
grammar
a single
G1
digit, right?
This
is kind of
Suppose
the last
the start
step,
symbol for grammar
do.
G2 is S2.
Or
let's say this is
it can
S2,
go to a digit followed
by S. Sorry, this is G2 and it starts with S2.
And since we want 4 digits
G1
in our number,
and G2 have disjoint sets of non-terminals. That means that
S,
all of the non-terminals in
is going to be S
this first grammar do not appear in the second one, and vice versa.
And
so
now, because we're trying to do a rightmost derivation, we need to expand the rightmost non-terminal first.
The non-terminals in here are S2 and
so that
A,
means that
and neither of them
going to
appear there, so we're good. And if I want the language that represents the union of both of these languages,
a couple more times,
right?
We'll
then
take those DDs
what I
and
can
we'll
do
expand
is
that
I
S
can say, all right,
DS,
well,
right? So
I'm just going to add one more
expanding
production
this
rule. You
S,
ready?
the
I'm going to put it at the very
non-terminal,
top. I'm going to stuff it actually
into DS
up here. And I'm going to say S goes to
expand
S1
that
or
into
S2.
D.
And if I do that and I take
this last
all
time,
of
I'm going to
these
turn
production rules together,
this S just into a D, right?
That forms
and then
the
again, we're
language
doing
that
a
is the
rightmost
union
derivation, so now we need to expand.
Right? So start
D here
and
on the
either
right.
go, after you start, you either follow this
So
path to
that's
create a
going to
language
go
that's in
to
a string that's in the first language,
D,
or this path to create a string that's in
one.
the second language, and the result
now we'll
is you end up
expand
with
the rightmost D
a string that's
again.
in the union of these
That'll
two.
go to D.
Okay, so in this slide, what we're trying to
O1.
do is we're trying to concatenate two languages,
sorry.
right? So we're trying to
Non-traditional notation,
we're trying
but
to
I'm running
have,
out of space. That will go to
instead of a string,
801,
the union of two
which
languages,
goes to
we're saying take one string from the first
7801.
language and one string from the
Okay.
second. Right? And I'm using the same two languages
here's
as examples again, so theoretically I can paste
a problem
those
from the book that
grammars.
is equally
So here you go. Here's the grammar from the other
easy.
slide.
It's just a little bit painful.
In blue,
So we have this grammar, right, which is a grammar
for the first
of
language. And
braces,
in
it looks
purple,
like, right?
I have
Square
the grammar
braces.
for the second
square
language,
brackets,
so
you might want to
second
call them,
language
right?
grammar.
And S can either go to
And what
a
I want to
lambda
do is
or
instead of having strings
S followed by
that
square brackets
come
with
from
an S inside.
either the union,
And
I
it
want
says
to
for
do
each of the following
concatenation,
strings,
so I
construct
want
a
all my
leftmost
strings
derivation,
to
a rightmost
start
derivation,
with,
and a parse tree.
A to the N,
Okay,
C to the
so
N,
let's do this
and then
first one
end
first.
with B to the M, A to the N, right? And again, this is pretty
Shrink that
easy
up
if I just
there a little
add
bit.
one more step
So
here.
I want to do, let's do a
S
leftmost
goes
derivation
to S1, S2,
for
then you'll see that this whole
all right. So leftmost derivation.
grammar in
Well,
here, if
we've
it's
got
taken
S,
as a whole,
not much choice
represents
for
a
the first step,
grammar
right? That
for
goes
the language
like that.
that is G1
And then
concatenated with
the
G2.
first thing we need to do is expand.
Okay, so
the
one
leftmost
last
non-terminal,
way to, this is kind of the
this
the
guy. And
rules
since we
for
have nested,
quickly making grammars from other
square
grammars.
brackets here, that guy
in
is
this
just gonna
case,
go
we're going to
to
try and come up with how to do the
lambda.
star of a grammar. And so the question is, if you have a grammar G1 that
and now
starts
we
with
expound
S1,
the leftmost
how do you get a
non-terminal,
grammar
which is
for
the S in there? So
the closure
that
of
will
that,
go
the star
to,
of that grammar?
let's
And so, as
see,
an example
lambda
here,
bracket.
I said let's find a grammar.
We're going to have S bracket.
So big.
S.
A grammar for
that, right?
A, B
because
star.
what we've done is we've
So,
taken
a grammar for AB, of course, is very easy because that's just a single
into
a single string.
Piece. That looks right.
And this says, well, if you start with
and
S1,
now we're doing a leftmost
right?
And
so
I think
if you already have a grammar for
I just need to make sure I do it
thing
in the
that
right
goes
order since we're
inside
doing
of the
derivation,
closure, right? For
so
example,
that goes
here,
to
AB, that
lambda
starts with S1.
bracket. We'll replace
Then
that
to
S
turn
with
that
a lambda
into
bracket
another grammar
bracket,
for the language AB
which
star,
goes to
all you do is
lambda
this
bracket,
trick,
lambda
right?
bracket,
So we're just going to add that rule.
bracket.
We're adding the rule.
So there's our
S. Notice I'm
leftmost
putting it
derivation.
above
I'm
because
going to
I
leave
want
the
S to be my
rightmost
start
derivation
symbol.
of this one to you.
Goes
but
to
let's do a parse tree
S1,
for this. So let's see if I can
or
shrink
lambda.
this up a little bit.
And if you take these two
move it
rules
up, hang on.
together, I think you'll see
All right, we're going to lose the
that
thing
we
at
have
top,
the rule
I
for
think.
AB
There
star.
we go. Let's put that.
Pretty cool, huh?
Let's see, maybe if I shrink it a wee bit.
Okay, so just to wrap up.
Okay,
We've
so
talked
let's
so
just do a
far
parse
about
tree for this
grammars.
derivation we just did.
Just kind of
And our
generic
parse
grammars.
tree,
This is something
we
that
get the
you
S
didn't
at the top,
necessarily
right? And
learn
what I'm
in
gonna do
discrete
for this parse tree
structures,
is
but
I'm just going to
many people
step
will have
through
learned
each
already,
step
so
here.
it's in a much earlier chapter in the book than
I've
we're
got that
mostly
one
working
done. Now
in.
let's do this one.
But what we're doing
the
is
S
we've
goes
talked about
to
grammars in general
S
in this slide set.
bracket.
And in the next set of slides, we'll talk about
bracket, and you'll
a
see just like with
subset
our
of grammars
English
called
language
regular
parse tree that we
grammars.
did at the very beginning. The terminals end up as leaves on the tree, and we have to expand the non-terminals. So the next thing that we expanded in here was the S inside the bracket, right? And we were doing a leftmost derivation, so next we expanded this leftmost S into the lambda, and then we expanded this S into the S bracket, right? So we are up here now. If you just look at the leaves of the tree so far, that shows us what's in our sentential form, right? Again, we are going to expand the leftmost non-terminal. We're here. We expanded this one. We're expanding this one. So that goes to lambda, and then we do the next one, and that goes to lambda. So there you go. That is the leftmost derivation and the parse tree for that. Now what I'm going to do is why don't we just do the rightmost derivation for the second one, because it's pretty messy, and then I'll leave it to you to do the leftmost derivation for that and the parse tree for that. So let me clean up my screen. Hang on. And now we are going to try and do a rightmost derivation for it. It's open, open, close, open, open, close, close, close. Let's just see, did I get that right? Hang on. That's two opens and a close, so these guys are together, and we have these outer ones match up, and then we have a pair of nested ones there. Yep, that looks good. Okay, let's try a rightmost derivation for this. Right? We don't have any choice for our first step. We start with S goes to S bracket, S bracket. And then if we just kind of look at this, we can't put any more outer brackets in there, right? So these two brackets here represent these two brackets here. And this guy's going to go to a lambda eventually, except that we are doing a rightmost derivation. So maybe what I'm going to do, I'm just going to color code these a little bit. And I'm going to put a little red dot there, a little red dot there, and I'll put a little red dot there and a little red dot there just to remind me what we're doing. So we have to do a rightmost expansion anyway. So, and we do want some more brackets inside. So let's see what we get. So we say we're going to go to S. And that guy, like I said, that first S is going to go to a lambda, but not yet. And S bracket, bracket, oops, with an S inside, right? So these two are still that red one, And now it gets interesting, right? Because, let me get another color. This S here is going to represent this piece. And these two, I think, are going to represent this piece. Right? And now let's keep going. We have to do rightmost derivation, and we need another pair of brackets in here, right in here. So this needs to get expanded once more. So that goes to S bracket, S bracket. Now I'm going to expand this S into S bracket, S bracket, and then we put the final two closed brackets on. So just to color code it for our own use, right? The color code is not part of this. Those are the red outer brackets, and then inside we have the green brackets, and now we'll add a couple more brackets. We'll make these ones purple. All right, and these purple ones correspond to that, but we still have not done this piece here, right? But of course we need to go from right to left, so let's just look for a minute. We have bracket, bracket, wait, so we have the triple kind of bracket thing, right? And then we have the two out. So this one's going away, right? And then this one needs to expand to another set of brackets. So we can't expand this one to another set of brackets yet, but eventually, let's say, that's going to be the orange brackets, and let's make that orange instead of green. Okay. So again, we're doing a rightmost derivation. So we need to expand this S. So we will expand that one just into a lambda now, because that's kind of done. So that's going to go to, actually let's go to the next line. Start writing smaller. It's going to go to S bracket, S bracket, S bracket, lambda, bracket, bracket, bracket. Great. And now we need to expand, do rightmost expansion again. This one corresponds to that one, which is just another lambda. So that goes to bracket S, bracket, lambda, 1, 2, 3. All right. Now we are up to what I think is our orange one, right? So that needs to expand again into another set of brackets before we get rid of it. So we have bracket, and we're going to expand that orange into S bracket, S bracket. And then we copy everything else that we have. Bracket, lambda, bracket, lambda, 1, 2, 3. I am completely running out of space. Hang on, let me see if I can shrink this slightly. I think as I shrink this, I'm going to end up messing up some of these lines up at the top, but bear with me. Let's see what happens. Yeah. So ignore the lines way up at the top. Okay. And let's see. So, and I'll try and write more small. So we're doing rightmost derivation. So now we need to reduce that one. Well, so we will do bracket S, bracket, lambda, bracket, and then we've got the bracket, lambda, 1, 2, 3. And rightmost derivation, we only have one non-terminal left. So we go to bracket, lambda, bracket, lambda, bracket, bracket, lambda, bracket, lambda, 1, 2, 3. And I'm really hoping that when I get rid of the lambdas, I have, I'll just write an equal sign there, right? 1, 2, 1, 1, 2, 1, 2, 3. Hurrah, I think we did it. And again, you could do a parse tree for this, right? It would start out by saying, let's just look at the first couple steps. We had our S, and that went to S bracket, and then we would expand this one and so on. This one, right? I'm not going to do that parse tree. You can do that as an exercise. Of course, we said that if you have an infinite language, you have to have a some sort of way to derive the longer strings. That comes from recursive productions. We say a production is recursive if the left side appears on its right side. So, for example, here we have S goes to AS. We can also say it's indirectly recursive if there's a couple of steps that get us back to where we were. So here we have S goes to little a, but big A goes to BS. So eventually we get back to that S. Whoops, and I think I gave away my answer to this question here. A grammar is recursive if it contains at least one production that is recursive or indirectly recursive productions. So are all grammars for infinite languages recursive? Yes, of course they are.